Module 5, Objective 6, discuss the factors that affect the speed at which action potentials are propagated and the differences between continuous and saltatory propagation. Propagation, again, is defined as the movement of an action potential down the length of an axon. And there are two types of propagation, continuous and saltatory, where saltation refers to the word jump. Continuous propagation occurs in unmyelinated axons. Remember, myelin is a fatty sheath that is found in some of the glial cells, either the oligodendrocytes or the Schwann cells that were discussed in a previous objective. With continuous propagation, you're going to affect each segment in turn. So step 1, the action potential develops at the initial segment of the axon through the depolarization of the transmembrane potential to threshold. Step 2, the local current develops and it's going to depolarize the second segment to threshold. Step 3, the action potential occurs in the second segment and the initial segment is going to repolarize. Step 4, the local current depolarizes the next segment. And that cycle is going to repeat as the action potential travels down the length of the axon. And it does so in about 1 meter per second. So if we were to see a visualization of that, here in the image we have 3 segments of this axon. And as the action potential develops in segment 1, the membrane potential at this site depolarizes to plus 30. Step 2, the local current then develops as the sodium ions enter at step 1, spreading along the open from the open voltage gated channels, and a graded depolarization quickly brings the axon membrane in step 2 to threshold. So with continuous, you're going to basically move from segment to segment. This is going to undergo depolarization and repolarization, followed by the second segment, the third segment, the fourth segment, all the way down the length of the axon. Step 3, an action potential now occurs in segment 1, while segment 2 begins to repolarize. Step 4, as sodium ions enter at segment 2, you're going to get a lateral spread. A graded depolarization quickly brings the membrane in segment 3 to threshold. And that cycle is going to continue all the way down the length of the axon. Saltatory propagation occurs in myelinated axons, and it's faster than continuous propagation. It's going to require less energy because the myelin prevents continuous propagation. And because of the presence of the myelin, that current has to jump from areas of the axon that are identified as nodes. So they jump from node to node. And depolarization only occurs at those nodes. Let's look at an example that might be a little easier to follow. Here we have the cell membrane of the axon. And we can see these regions of myelin sheaths. They literally wrap around the axon just like you would wrap electrical tape around an exposed wire. And what myelin does is that it insulates that region of the axon. So nothing can occur here. No ions can move in or out because it is literally insulated with this myelin. So the only regions that allow for the movement of ions in or out of the cells are these regions here and here and here and here. So essentially you get this jumping that occurs over these myelinated regions. And because all that area is skipped or jumped over, the myelinated axon is going to transmit an action potential quicker. And again, the same steps are occurring. You know, you have your depolarization followed by repolarization from segment to segment. So it looks the same as continuous, except we now are jumping over these insulated regions where the insulation is myelin. So it happens at a quicker rate. In addition to the presence of myelin affecting the speed, we can also look at the diameter of the axon. So if we have two axons that are the same length, but one is considerably larger in diameter, we see that the larger diameter has a lower resistance and therefore a faster speed. So this is faster. And the simplest way that I can explain this is, consider this. We have a ton of potassium inside of this cell. It is crowded with potassium ions. And then we have sodium ions on the outside. And again, there's quite a few of them. When channels open, sodium rushes in, but it's already crowded in there. So that's going to slow the depolarization of that cell. It's going to slow the flood of sodium moving into that cell. When you have a larger diameter, sodium is going to be able to move in just a little easier because there's not as much crowding as you experienced with the smaller diameter. So that's going to lower the resistance and therefore allow a larger diametered axon to propagate an action potential quicker.